So the next task is to convert polar equations into rectangular equations. This is often a little bit harder, and the reason is that we have these conversions. We know that we've already seen that r sine theta equals y, r cosine theta equals x, and we can also make use of r equals the square root of x squared plus y squared. So we're going to try to do is convert equations into equations in polar coordinates into some combination of these forms, and usually that requires a little bit of algebraic manipulation, sometimes not too much. So let's see. Let's try the first example. Let's consider r equals 7. Let's convert this into rectangular coordinates. We see is that we can replace r with the square root of x squared plus y squared, and so that's going to equal 7. You may recognize that if I square both sides, this just gives us x squared plus y squared equals 49. That's the normal way that we would write this. And what that's going to be is the circle whose radius is the square root of 49, or 7. So this is just a circle of radius 7. And this sort of makes sense because if you think about it, what I was given was the equation r equals 7. That's a constant function. In other words, give me any angle and I will give you a point that's exactly 7 units away from the center. Well, that's exactly what a circle is. A circle is the set of all points. A circle of radius 7 is the set of all points that are a distance of 7 away from the center. So it sort of makes sense that when we come to the familiar rectangular form of the equation, x squared plus y squared equals 49, that it would just turn out to be the circle of radius 7, or the set of all points that are distance 7 from the center. Okay, so let's try another one. Let's do r equals 2 sine theta. Okay, so here what we want to do is we have 2 sine theta, but what we need in order to handle that sine theta is we need r sine theta. So what I want to do actually is multiply everything by r. I'm going to multiply both sides of the equation by r. That gives me r squared equals 2r sine theta. And I know, by the way, what some of you are thinking. What some of you are thinking is, wait, what rule told me to multiply by r? Um, this is the point where I sort of have to level with you that being good at this sort of thing involves having a little bit of a thirst for just playing around with expressions. And, I only know how to do this because, I've taught this class a number of times. How did the first person think to multiply by r to get this? I'm not really sure. All I know is that the trick is going to be to try to get an r sine theta or an r cosine theta to appear in the equation. So it sort of made sense to do that. Okay, so now I have r squared equals 2r sine theta. So this is going to be the square root of x squared plus y squared squared. It's equal to 2, and r sine theta is y. Okay, so I now have x squared plus y squared equals 2y. This gives me x squared plus y squared minus, let's see, minus 2y is equal to 0. Now, let's see. So you should recall how to complete the square. So this is going, let's just come up here. This is going to give us x squared plus y squared minus 2y is going to be y minus 1 squared minus 1. That's if you don't, you can look up, I think in the beginning part of the book, in chapter 1, what the algorithm is to complete the square. You can verify yourself that y minus 1 squared minus 1 is in fact the same as y squared minus 2y. The point is that I can replace this with this. So that gives me, I still have to put in the equals 0 because it's still an equation, and having replaced this expression with this one, the whole thing should still equal 0. Okay, so this gives me x squared plus y minus 1 squared is equal to 1. This is, in fact, the circle. This is the circle whose center is 1, 0. Center is there, and it has a radius of 1. So I'm looking at actually this circle. Okay, so that's what r equals 2 sine theta. R equals 2 sine theta produces this graph in polar coordinates. Okay, just for the last example of converting polar into rectangular, I just wanted to show you this problem, which if you try to do it without really thinking about it, it becomes harder than it looks. Let's suppose that I have the polar equation theta equals pi over 4. Let's convert this into rectangular coordinates. If you try to apply these conversions, you're just going to get lost because none of them will really apply. I mean, okay, so the last example that I want to do of converting polar into rectangular is this one. Theta equals pi over 4. First, I just want to show you the easy way, and then I want to show you the kind of absurdly formulaic way to do this. So the thing to recognize is that this is just going to be the set of all points that lie on the line that makes, or the ray rather, that makes an angle of pi over 4 with the x-axis. So if you think about it, what this equation is saying is just that it's the set of all points that of any radius that lie on this line. In other words, this line of pi, where the angle is pi over 4. Well, you can certainly see that a 45-degree angle is going to make the line y equals x. Okay, so if you really just think through it and think what this equation is telling you in those terms, this simply becomes becomes the line y equals x. Now let's suppose that you can't remember that. You really want to try to do it with these formulas. I'll show you how to do that, although I encourage you to simply reason it out the way that I did. So uh, what I can do is I can take the tangent of both sides. So let's take the tangent of theta is equal to tangent of pi over 4. That gives me tan theta is equal to 1. We know the tangent is sine over cosine, so that gives me sine theta over cosine theta equals 1. I can multiply this by r over r, and that gives me r sine theta over r cosine theta equals 1. Since r sine theta is y and r cosine theta is x, that gives me y over x equals 1. And finally multiply both sides by x, giving me y equals x. So this is the answer. I think it's easier to do this by simply thinking about what the equation means. But if you really can't, you can do it this way, where it actually does work with the formula. There are certain important shapes and curves that are just worth knowing what the equation in polar coordinates is for them. So I just want to give you a list of those. These are things that you really should commit to memory, and especially if you're going on to Calc 3. There are a couple of things that, especially from Chapter 11, think back to the parametric curves, that you really need to know. Some of them are, for example, the equation of a line in parametric form, which we did earlier in the chapter, but the other ones are these particular equations in polar coordinates. So which is not to say that you don't need to know them for this class also. I'm just saying the reason you need to know them for this class is that you will hit the ground running in Calc 3 if you know these as well. So okay, so first of all, the circle with center at the origin and radius a is just the equation r equals a in polar coordinates. Vertical and horizontal lines in polar coordinates. The vertical line x equals a is r equals a secant theta, and the horizontal line y equals b is r equals b cosecant theta. So the next one, sort of surprisingly, is we did one example. We actually did the second one of these, the one that's r equals 2a sine theta. We did a specific example of that earlier. This is what I call an offset circle. In other words, it's a circle of radius a whose center is either at a0 or 0a, as I've drawn them in these two examples. So in the first case, when the center is at a0, this is going to have the equation r equals 2a cosine theta. And in the second case, where we have a center of 0a, a little bit up the y-axis, the equation is r equals 2a sine theta. And then finally, we saw the previous example where for a line through the origin, this is just going to be theta is equal to the angle that the line makes with the origin. So one way to describe that is the line through the origin with a slope of m equals tan alpha. The equation of that is theta equals alpha. And by the way, that's really what we had done here when we solved this problem. we were given theta equals pi over 4, and we simply converted that into the equation tan theta equals 1. So in other words, tan theta equals the slope, and from there we were able to get the rectangular equation of the line. So you can see them all if you want to study that. I'll just put that up